Yay. At least I figured it out last time. It didn't take me forever. Okay, where are we? Yeah. So, got a problem there that you're working on. Oh, I do one last time. I'll just blow my nose here. So, oh, there's somebody else anyway. Yeah. I think I'll distribute first. All right. I'm hoping you're almost done. A bit ahead of me here. So what do I get here? 60x's minus 30. 30 of this, 30 of that. 50x's, yeah, plus 40. Bunch of tens, huh? So far, so good. Now, choose sides. Well, which side do I want to move all the variables to? Which one for the constants? I think I'll move all the x's over to the left. So I have to subtract this term. All 50.
So can I just inquire why that decision was made? I just love to know why these steps are chosen to make instead of doing like we were doing before, where we would have gone, minus, it would be, 60x minus 30 plus 30, and we would have added the 30 to the other side. Why are we choosing to use the variables instead?
Oh, okay. That's actually a good question. It's totally arbitrary which I decide to move first. I do want to get all the variables to one side and all the constants to the other side. I don't know what it is in my mind. I just sort of naturally jump to, I'm going to move the variables first. I could move the numbers first, but the point is I've got x's on both sides and constants on both sides. I'm really just moving them together like sides and not really doing any solving steps, you might say. I'll do it the other way, actually. It doesn't make any difference. I could do this first. Absolutely. Okay? But next step, I'm going to move the variables. Good point, I've been stuck on that other process, just where my mind went to. So if that works, if that's okay with you there, I'll continue like this. And that means I have plus 70 over here. Yeah, good for me to do it the opposite direction. Good point. But now I still have x's in two different places. All the constants are over here. So I'm going to do what I need to do to collect all the x's onto the left side, which is subtract. Now I'm going to subtract these 50 from both sides. Is that okay? I wasn't sure. Was that Glenn? Yeah, who asked that? Was that okay? Okay, good. She gave me a nod over there. And that reminds, I'll finish this. One last step, obviously, right? We're going to divide both sides by 10. 7. Yeah, as I was closing up yesterday, I noticed, a couple of you had submitted chats. Basically, you could talk to each other, or hopefully I'll hope that I see it eventually. And I think it might have been that one of those problems we were doing, and I got to this point, and I turned it into 1/3 right away, and somebody asked, why not just leave it like that? But one of the chat comments was, a high school teacher once said, if you don't simplify it now, you'll have to simplify it at the end. I almost said that. Absolutely. If I leave it like this, I probably get an answer that's twice as big as I would if I simplified it first. It really doesn't matter. It's kind of a now or later thing. Just a little tangent there, but I just wanted to appreciate that comment that somebody made. See if that makes any sense to you, since I just did it out of the blue. All right, is that all right? Here we go. On to the next. Do another one. And got a couple ready to go here. We're into the messy section here, 2.4. So here it comes. I call it messy when you got a lot of simplifying to do. You're just careful and follow this, the right steps. You'll get there. Uh-oh, gotta squeeze it in. 3x minus 5. I'm gonna erase over here because this is a long one, okay? Just a bunch of distributing to do. Everybody was so eager to practice distributing more. There, bunch of pieces. Simplify first, even though I erased that. You get started. Simplify all that first. You're going to have to distribute, and then I would encourage you to just collect all the like terms within each side. You got pieces to put together on the left and pieces to put together on the right. Then worry about moving from one side to the other. One section of topics today. I think we have plenty of time. He says, I'm just going to distribute. Let's say you're that far already. Here I go. And double check maybe before you go any further.
Let us do the whole problem first before you answer it.
I know. I just want to do one step at a time. I was hoping maybe you were done with the distributing. I'll wait again. Okay. I'll wait again, but I was just going to say, watch out. Make sure you got plus 12 at the end. Blah, what a mess. Uh-oh. Ha. This is one of those weird ones, I think. Uh-oh.
I got a really strange answer, so I can't wait for you to answer it.
I was just looking at your little mental math. Here's what I was just, what am I thinking? I'm looking at putting the X's together, and here's 21 X's. Over here, putting the X's together, it's 21 X's. Already I know there's the same number of X's on both sides. They're going to go away. Either you're going to get the same numbers, which means one thing, or you're going to get different numbers, which means a different thing, which is what I ended up with yesterday. Classification. So if you got something that seems weird, you're probably right. I'm going to just combine terms, all right? Hopefully you're farther along. I'm not stopping you from doing the thinking. So here I'm going to put my X's together. And 12, right? All right. And over here, my X's together. And it's what? Minus 33. Hopefully you agree. You don't? Yeah, somebody needs a good strong eraser there. I can hear it. Scratch, scratch, scratch. So, any issues with simplifying? I just simplified on each side so far. Now I'm at that point, you hopefully are at that point, I'm going to decide to move all the X's or all the constants. Let's do what I think it was Gwen suggested. We'll move the constants again. How's that? Okay. I'm going to subtract these 12. You might have gone the other way. You might have added 33. It doesn't matter. If I do that, I got to that point. If you think about what you have already, red flags should start going off how can 21 times something be the same as 21 times something and then minus 45? How can those be the same thing? So already at this point, you know, this is not going to be normal if you recognize that. If I subtract, try to move all the x's, I get 0 is negative 45. No more variables, they cancel each other out, and I have this false statement. It's not true, and it's not dependent on any variable. There is no variable left. That's what's important about these couple weird conditions.
Is that what you call the contradiction?
Exactly, right? This is, and contradiction, again, I like to think of that as, oh, that's the, contradiction is a negative term, right? So this is the negative, the bad one, right? Contradiction. This type of equation is called a contradiction. How many solutions does it have? None. There's no way I could, all the x's went away. No matter what number I plugged in, it wouldn't have worked out. So no solution. You have no solution. There we go. All right. I picked that one out of the textbook problems and did not expect it to do that, but oh well, it did that right away. It went to one of our unusual ones. I did finish up quickly yesterday with this the classifications, these 3 different types. So this is one of the types called a contradiction, where you get no solutions. They usually kind of hide it in lots of work you got to do to boil it down to that step. If they just said this equals that, you'd say nope. If I'd gone through all of that work and gotten down to something, I'm just kind of changing the problem now, folks. If I'd gotten all the way down to something that says, you know, 25 equals 25 and no variables, I could subtract the 25s and even say 0 equals 0. If you did kind of the same thing and got that weird kind of answer, and it's true, but no variables, right? It's true, but no variables. This is called an identity. This side was identical to that side, right? Identity, any value for x would have made it true because the x's went away and they didn't matter, right? Infinite number of solutions. Okay, so there's the second classification. And then I mentioned the third type is the kind that we work with 99% of the time, where you get one condition, one solution, conditional. For this kind of equation that we're working with in our class, we only get one equation. We get messier, more complicated equations that do have more than one solution, but that's higher level classes, don't worry. So there, 3 classifications. And I know, I'm pretty sure you have one of those in a hand in homework assignment. You have a problem like that. It turns out weird. And I know in 2.4, there's at least one problem where they expect you to classify the kind of solution you got. Now, one thing that
A little confused on the difference between an identity and a conditional, just because it looks like 25 equals 25 is a solution. So can you give me an example of what a conditional solution would look like?
notice there's no, whatever variable this might have started with, it's no longer there. We're not saying that x equals 25. If I get something that says my variable equals this number, that's the value for the variable that makes it true. That's a conditional.
Got it. So versus having whole numbers equaling each other, it is a variable with a solution.
Yeah, this is
Got it.
what the variable will have to be to make it true. Here, there's no variables. They went away. They canceled out. So the variable was never mattered, right? No matter what variable I put in, it was always going to boil down to those two numbers are the same, or no matter what variable I put in, the variables canceled out And it was false. Yes, variable or no variable. If you have a variable left, it's got to be a conditional. If you got a variable, it's going to be equal to some value. It's going to be one solution. Okay, good. All right, here goes. Well, we're going to keep doing the same stuff, but we're going to throw in fractions and decimals. Look at, try and give you some good ideas on how to go about solving those kinds of equations. Maybe make them simpler for yourself. So 2.5 is what this is. Equations with fractions and decimals. 1/4 of x plus 1/2 equals 5/8. So notice here's our one term with a variable, an extra added constant, and it equals a constant. So the basic shape is not any more complicated than that, right? It's this basic shape, except it's got the fractions in it, which means we usually have to do a little extra work. Now, if you look, when we dealt with just fractions, trying to simplify them or put them together, add and subtract, we would come up with common denominators so they were the same size pieces and we could combine them if we wanted to. These numbers aren't too crazy. We could come up with a common denominator and just work with the fractions in the problem just the way we do add and subtract, multiply and divide in all the previous problems. But the technique, if you like doing that, if you're really comfortable with the fractions, you may go ahead and do that. But the technique that we usually teach is getting rid of the fractions. Imagine if I have, this thing equals this thing, in some equation, whatever those two things are. Well, if I multiply both sides by 3, well, then 3 of these things is still equal to 3 of those things. I can make everything equally bigger, and it's still balanced. It's kind of the abstract thing I'm trying to get at. Math with shapes. It's kind of like section 2.6, right? Those of you who've been there. All right, so I'm going to multiply both sides of the equation by some number that's going to make everything big enough that it's not a fraction anymore. Let's think about that. I'm going to make everything bigger so that these aren't fractions anymore. What number do I want to use?
So do you subtract the 1/2 from both sides? And then do you have to change the denominator to an 8?
Okay, I'm saying no, I'm not going to do that.
No? Okay, yeah, I'm confused then.
I'm just talking it through and I haven't done anything yet. Okay, I'm not going to try, I'm going to get rid of the fractions. I'm going to turn this into a problem that doesn't have fractions in it. All right, so I'm trying to describe how I'm going to get rid of those fractions. I'm going to multiply everything and make it all bigger. So you can imagine if I multiplied this piece by 4, it'd be 1x again, right? Or if I multiplied this by 2, it wouldn't be a fraction. If I multiplied this by 8, it wouldn't be a fraction anymore. The denominator cancels out. Well, I got to multiply everything by the same number. So I'm going to find the common denominator. What's the lowest common denominator? In this case, the common denominator would be an 8.
Okay.
But I'm not going to get a common denominator. I'm going to multiply every number on top by 8. So here's what I do. I write it like this. I have to multiply every piece times the same thing to make them all proportionally bigger. So this is what I'm showing, 8 times those 2 terms. Now you can do this in your head when you're comfortable with it, but I'm just going to show everything. 8 times this gets me to 8/4 of x. And 8 times this gets me 8/2. It's like, wait, that's still fractions. Give me a minute. And this becomes 40/8. You see how we're going to cancel that one. Now these, if I did pick the right number, these should simplify to numbers that are fractions. Oh, 8 over 4, that's 2x. 8 over 2, that's 4. 40 divided by 8 is 5. By multiplying everything by 8, I made them all big enough that they weren't fractions anymore. Now it's just like all the other stuff we've been doing. Notice I was just really multiplying the numerator.
So instead of treating them like fractions, inevitably you're treating it just like division, correct? Because if you were to take that 8 over 4 as a fraction, there would be no simplification of that.
Right. I'm showing that I didn't want to skip any steps, right? I'm showing that, yeah, 8 times this fraction is like 8 over 4, and it reduces, right? 1 and 2, it reduces to 2. I don't like canceling out at this step because I still have to do the entire 8 times the next piece also. I like not showing.
Okay, that really confused me, so maybe I need to go back and do that cross-canceling.
Okay, so, right, 8, if I do 8 times 1/4, I get 8/4, and it reduced, right? 1 over 2, it reduced to 2. If I do 8 over 1 times 1/2, I could say, oh, I got 8 halves, and then I reduced it to 4. And here you could just say, oh, look at that, right? I get the 5. Now, once I've got, we'll do this a couple times and see, hopefully it sinks in. I'm going to solve this. What, 1? Divide by 2. Oh, it started out as a fraction problem. I got a fraction answer. Okay.
Okay, so are you saying that if I subtracted the 1/2 from both sides and just continued the problem like that it would be wrong?
No.
Okay.
I was trying to get you to watch the technique I was presenting.
So this is just like a second way of doing it?
Okay, yeah. Now, let me do it. By the way, if I wanted to do that, if you want to deal with all the fractions, subtract the 1/2. And I'll get to 1/4 x equals 5/8 minus 1/2. Now these fractions are not that messy. I could build common denominators. I could get these both to be 8s. This one I could solve pretty easily with all the fractions. But I'd have to get a common denominator here. Eventually I have to multiply by 4 over 1 on both sides to cancel that fraction. But as they get more and more complicated fractions, it'd be kind of nice to get rid of them. Are you okay with the idea that yes, this is okay if you want to keep going this way, right?
I am just wholeheartedly, completely confused by this equation and how to do these steps.
Well, what do you want to do? How do you want to solve this?
In my mind, you know, I was trying to go along with your idea of doing the 8 over 1, you know, times the 1/4 x plus the 1/2. But after that, that's just where I'm completely stuck. It just doesn't seem to make much sense.
Okay, if I have 2x equals 4, and I multiply both sides by 3. I've come up with an equivalent equation, you could say. I just made both sides 3 times bigger. I could still divide by 6. I got x equals 2, just like I would have up here, x equals 2. I didn't need to do it there.
I feel comfortable when it looks like that, but when we get into doing it with fractions, I don't know why. It seems to be just very, very confusing, and I'm not, for whatever reason, following the steps that you're laying out for us, and I don't know why.
I'm doing these steps to clear the problem of fractions so that I don't have to work with fractions.
Can you turn the 8 into a fraction and work the equation from that way?
You mean you want me to write it like this?
Yeah, like 8/1. Yeah,
Oh, yeah, all right.
please. And just go very slowly, step by step, as to how we would even approach the next steps to this.
I guess I was thinking you could follow that distributing that I was doing the other way. Okay, so here's 8/1 times that and 8/1 times that. Is that okay?
Yes.
Now, if you want to cancel at this point, fine. I was trying to be careful not to do too many steps at once. I wrote it as 8/4. That's what I did. And then I simplified. But if you're comfortable here by saying, oh, I can divide these both by 4, then I get 2x.
Okay, I'm following you there. Next step.
I can divide these both by 2. And I get 4. Or 2/1 or 4/1. You know. And here I can divide these 8s and I get 5. So maybe I was not showing the middle steps the same.
Okay, thank you so much. I just absolutely could not fathom how you got from there to there without you writing it out like that. So thank you.
Okay, and just I could see how, you know, fraction next to a fraction, I should make this look like a fraction, good. And without doing the canceling, see, I don't want to cancel right now. What happens if people try to cancel here? Oh, there's only 2 left to multiply the next fraction. That's not true. You have to multiply the entire 8 times the next fraction.
I think when you go to solve the problem and you skip those steps, it's kind of confusing for some of us that need that extra explanation to even understand the fraction part of the work in the first place. I think some of us struggle with fractions as a roadblock specifically.
Yes, well, okay, so I was thinking I was showing enough, but obviously not. I was showing 8/4 by multiplying 8 times that first fraction. And okay, we'll do it again. Here we go. So, all right, now this one doesn't have a fraction in it. But here's x plus 3/4 equals 1/2 x. If I had to subtract, if I wanted to try to subtract the x's and add, or get all the constants, well, I'd have fourths. I could put the constants together. I'd have x minus 1/2 x. I really have to think of it as 1 or 2/2 minus 1. You know, if you are comfortable enough with the fractions, you can do that and make it work. But if I get rid of the fractions, then we're dealing with the whole numbers or the integers, and it usually goes better for lots of folks. So I start by thinking of what is the common denominator of the fractions that I want to multiply everything by. Well, looking at the fractions, you can really think of this as over 1. The lowest common denominator is a 4 for all the fractions. So now I'm going to multiply every term times 4. I'll write it as 4/1. So the first step is pick the number you want to multiply everything by, and it's the common denominator. All right, now I'm going to distribute. So I get 4/1 times x plus 4/1 times 3/4 is 4/1 times 1/2 x minus 4/1 times 1/4. There, did I do better that time?
Yes, thank you.
All right, now I'm ready to simplify each term and try to reduce it to a whole number. if I pick the right common denominator number. So here I just get 4x for the first one. Here I did this, the 4's cancel out, so I get plus 3. Here I'll divide by 2 and get 2x. And here the 4's cancel and I get minus 1. So I made each term 4 times bigger, and that made them all big enough to get rid of the fractions. Now I get to pick which side do I want to go on. I'm going to move my variables. I'm going to move this 3. I'm going to go sideways here. 2x equals negative 4. And divide by 2. X equals negative 2. Checking the clock there.
And that answer would be conditional, just the one answer.
Yes,
Okay, thank you.
that's right. That's what I was about to say before somebody had a question. You don't have to classify every equation on every homework problem. If they ask you to classify it, then classify it.
I just think that going over these answers and just like kind of talking about it helps me learn like which one is which, I guess, just practicing that.
Okay, I say that because I guess it was when we used to be in the classroom and, you know, there was textbook problems where you worked them all out on paper and then handed in your homework to me. When we would do this section, people would try to say conditional or contradiction for every homework problem on the assignment. And it's like, well, you know, you really just needed to practice it on a couple of them. No problem. Yeah, absolutely. Conditional. Another one. You want to try it? I would pick a lowest common denominator to use. It's very similar to the last one.
So when distributing the 6, that would become like 6x plus, and then do you multiply just the denominator? So it would be 1/18th, or would you do both the numerator and denominator for it to be 6/18.
If I'm distributing 6 over 1, I don't get any 18ths.
Oh, okay. That makes sense. Thank you for writing it like that. That's what I should be doing differently.
You know, in particular, I'm picking the number and I am just multiplying the numerator in effect, the top of the fraction. So I get that top big enough to cancel out the denominator. This is kind of what we're doing. We're making all the tops of the fractions proportionally bigger, and then that, but by a special number that allows all the denominators to cancel out. So we're never multiplying the denominators in this process.
This is actually starting to make sense. Thank you for taking the time to just go through it slowly.
Sorry. Otherwise. I know fractions are one of the main places where people's understanding, when they tried to learn it before, kind of starts to break down. And once that happens, when you have trouble with fractions, it's real hard to be successful with the material that builds on it after that. So yeah, we gotta work fractions in along the way. Is that okay? Is that one okay then? So boiled it down to x equals -1. All right. And all right. Well, how about whoops, that's supposed to be a 2. Funny looking 2. I'm going to rewrite that one. See if I do. Just too far over here on the board. Couldn't write it well. Wait a minute, that's decimals. Decimals are just a special way to write fractions. Again, you could add, subtract, multiply, divide with decimals, especially since you get to use your calculator. That might not be too complicated, too tough to do. But imagine if you were required to actually do it all by hand, which we used to, like I keep saying, in the classroom, or before we were dependent on mom, and you being at home knowing you're always going to use a calculator, you would be expected to be able to do this without a calculator. So the technique is really similar to the fraction technique, which is let's get rid of all the decimals by making all the numbers bigger, multiply by something that makes them all not be decimals anymore. How do we choose that number? It's really kind of like the lowest common denominator, or what's the largest number of decimal places in any of these? Or what's the denominator, right? Tenths, hundredths. This is like 14 over 100. This is like 12 over 100. This is 35 over 100. This one's like 24 over 10. Right? Hundredths place, hundredths place, hundredths place, tenths place, and then drop the decimal. So what's the common denominator that I'm going to multiply them all by the same thing? I need to multiply them all by 100. I need to multiply them all by the biggest denominator here. Nicely with decimals, they're all powers of tens, and they're not, you know, 3s and 5s and 6s and numbers like that. I'm gonna, okay if I get rid of that was just comparison, you might say. So I'm going to do the same thing, and here I don't think I need to write it like a decimal, excuse me, like a fraction. And again, nice thing about multiplying by powers of 10, multiplying decimal values by powers of 10, you can, if you're comfortable with it, of course you can plug it in your calculator, but it's just how many zeros means how many places do I move that decimal point. Right? If I do 100 times 0.14, I move it over 2 places. 100 times that number turns into 14x. Is that okay? So 100 times this next number is just 12. 100 times 12 cents is now $12. 100 times 0.35x is now 35x redistributed. Now this one, there's only one decimal place, so if I've got to move it over 2, so I'm going to have to add an extra 0. So 100 times that one is 240, right? 2 places. Got to put in the 0 to get 2 places there. We haven't done a lot with decimals. Does that sort of relate to the fraction stuff? Does that make sense? Hope I didn't lose you there. Okay. But that's how we would get rid of the decimals in an equation problem like this. Multiply similarly, kind of like the common denominator of all the decimals was 100 would be the number we need to use. And so now I'm moving things around and solving like before. How about, let's see, there's lots of x's here. And so we'll do this way first here. How's this? I'm going to add 240. Just to do it the other way around, 252. So now I will subtract the x's. So 252 is 21x. Is that right? Did my arithmetic there, right? So dividing, yeah, the x's happen to be on that side. Divide by 21. Little mental math says 22, but you can plug that in your calculator or practice long division, right? One of them goes into 25, that, right? 1 times 21, line it up, subtract, you get a 42. Oh, 2 of them goes into 42, works out evenly. X equals 12. So similar to the fractions, the idea here is to clear it of the decimals. Do it again if you're ready. I'll just give you a second, give me a minute here to be ready. Is that all right? Stop me if. Yeah, do another one of those. Okay. 65 hundredths of x, right? 0.65. 1/10, 0.1. 4/10 x, 1 decimal place, and 35 hundredths, 2 decimal places. What's this largest denominator I've got to use? What's that power of 10 that would move it over for all of them? Well, I got 2 places, 1 place, 1 place, 2 places. I need to use the 100 again. Maybe my examples are too narrow tracked there, but you know, if you had 3 places, you'd have to multiply everything by 1,000, right? Or if everything only had 1 decimal place, then you just multiply all by 10, move it over 1. So I'm going to multiply everything by 100. Make sure I copied correctly. That's really sad that I try to give you at least really good partial credit when you're doing a hand-in homework or a test problem, and I can tell you miscopied it on your scratch paper. No way you're going to get it right. You copied it wrong. You did all the right work with what you wrote down. Anyway, I do not take note of that. It's unfortunate. So, all right, now 100, distribute that 100 to each of those. 2 places, right? 1, 2, 1, 2, we get 65x. 2 places here, I'm going to need the extra 0. And similarly over here, I'm going to need an extra 0 in there, 40x. And minus point, oops, no more decimal. Minus 35, 2 places. Boy, these are kind of nice numbers here. They're these examples. I'm going to move my x's. And add the 10 to both sides. Right, all these decimal problems turn out to be -1. No. Just a coincidence. These are examples of problems out of the textbook that I copied down as examples. Write down to work out in class. Got -1 again. Clearing it of the decimals to make it nicer numbers perhaps to work with. All right, now this will get you through 2.5. I'll go back and double check and look at the mom problems and make sure they don't get any trickier, okay? But we can come back and do a couple more of these tomorrow. Our last section in chapter 2 is solving a formula. Like imagine that perimeter is 2 length plus 2 width. Well, what if we just have the formula and we want to get the W alone? Move things around. It's all the same rules and processes. Unfortunately, something about more letters than numbers can be confuses people. But we'll do that tomorrow. But yeah, we can touch base on this again, especially if you try it and you come up with questions. All right? So I'm going to leave you for today, and you guys give it a try, and I'll see you all tomorrow. Okay?
Thank you for all of your help today.
You're welcome.
Yes, thank you. Have a great day. Take care.